All right, so today we are going to do applications of our trigonometry, and we're going to take a look at simple harmonic motion, damped motion, and combining waves. So our first learning objective is to build a model for an object in simple harmonic motion. So whenever we have vibration, simple harmonic motion is a special kind of vibrational motion in which acceleration A of an object is directly proportional to the negative of its displacement, D, from its rest position. That is A, which is acceleration, equals negative K times D, where K is greater than 0. So if we graph the distance of the motion and relate it to the unit circle, in this case it's not a unit circle, it's a circle with radius A, our theta is equal to omega t. Let's hold on. All right. So our x value is, if theta is equal to omega t, our distance x is equal to a cosine theta, which is equal to a cosine omega t, and that derives itself from cosine being opposite over hypotenuse, and opposite being x, hypotenuse being the radius. And our y coordinate is a sine theta, or a sine omega t. So make note of those formulas because we're going to use them to. So here's how to solve the problem. So here's how the spring motion models a trigonometric wave. So you have kind of a neutral position here. You stretch the spring and the distance increases. The spring compresses and it decreases and it goes back down. So to describe simple harmonic motion, an object that moves on a coordinate axis so that the distance d from its rest position at time t is given by d equals a cosine omega t or d equals a sine omega t, where a and omega are greater than 0, are constants. Moves with simple harmonic motion. The motion has amplitude, absolute value a, and period 2 pi over omega. Make sure you guys get these down because they're going to give you pieces and you'll have to put it together. All right, so frequency. The frequency is equal to omega over 2 pi. And just remember, omega is greater than 0. Okay, so now here's how we take the simple harmonic motion and solve the problem. Suppose that an object attached to a coiled spring is pulled down a distance 5 inches from its rest position and then released. If the time for one oscillation is 3 seconds, write an equation that relates the displacement d of the object from its rest position after time t in seconds. Assume no friction. So we're going to start with d equals a cosine omega t. All right, so let's start putting things together. We know that a is -5 because we pull it down 5 inches. Our period is 2 pi over omega, and that is given to us as 3 seconds. So 2 pi over omega equals 3. So omega has to be 2 pi over 3 if we multiply both sides by omega and divide by 3. So our equation is -5 cosine 2 pi over 3 t. And we look at the write an equation that relates the object, the displacement of the object from its rest position. Assume no friction. All right, next learning objective is to analyze simple harmonic motion, which I absolutely love because this is definitely real world. The voice I'm using right now is simple harmonic motion. So suppose that the displacement d in meters of an object at time t in seconds satisfies the equation d equals 25 cosine 4t. Describe the motion of the object. What is the maximum displacement from its resting position? What is the time required for one oscillation? And what is the frequency? So definitely we want to, so here's the words. Make sure you put a descriptor. How are these words related to the formula? To make sure at the end of this problem you know how to get from words to the formula. So A, and it says ask us to describe the motion. The motion is simple harmonic. B, the maximum displacement is the absolute value of A, and in this case A is 25, so the absolute value of 25 is 25. C, time required for one oscillation is also known as the period. So definitely should highlight time required for one oscillation equals period, because we have been using period and they are saying time required for one oscillation in these problems. And I don't want that to slip by you. I want you to know how to use that information in the problem. So a period is 2 pi over omega. You look here at the formula and omega is equal to 4, so it's 2 pi over 4. So a period is pi over 2 seconds. It's time t in seconds. And the frequency is omega over 2 pi, which is, omega happens to be 4, over 2 pi is 2 over pi oscillations per second. I noticed the difference between period and frequency. Period is how long it takes for one oscillation, and frequency is the number of oscillations per second. So they're like inverses of each other. This is how many oscillations happen in a second. This is how many times we, this is how long one oscillation takes. All right. Now we're going to do damped motion because we live in the real world. In the real world, we have gravity. So when we bounce, or friction, when we bounce a ball, it doesn't continue bouncing forever and ever. Eventually, it stops. It gets smaller and smaller. So we have what's called damped motion. Damp motion is the displacement d of an oscillating object from its at-rest position at a time t, and it's given by this herky-jerky looking formula. D of t equals a e to the negative b t over 2m. So this is all in that exponent, times the cosine of the square root of omega squared minus b squared over 4m squared t. Now, some scientists spent a lot of his time or her time coming up with this equation to describe damp motion. If you guys are okay, I would like to skip the proof and the discovery of this equation, and you can just say, yes, I accept this as the equation for damped motion. No, I don't need to spend what scientists spent years on going over the proof of this equation. If it's something you're interested in researching, you can do that, but for the sake of this section in our learning objective, it's not necessary. All right, we're going to analyze the damped vibration curve. D of t equals e to the negative t over pi cosine t, where t is greater than or equal to 0 because, yeah, it doesn't make sense for time to be less than 0. So if we take a look at these two pieces, and just the absolute value of these items, you can take the absolute value of d of t is equal to the absolute value of our function. And then it's true if you take a piece of the first piece and put it under its own absolute value, and then the cosine t under its absolute value. When is this statement less than or equal to 0, or less than or equal to? So instead, let's look at this damped motion problem here, which will give you a good idea of how to use the formula given information. So we're going to analyze the motion of a pendulum with damped motion. Suppose that a simple pendulum with a bob of mass 10 grams, that's important key, so write m equals 10 grams, and a damping factor of 0.8 grams per second. What letter did we use for damping factor, D or B? B, so B equals 0.8 gram per second, is pulled 20 centimeters from its at-rest position and released. So displacement at t equals 0 is the amplitude. The period of the pendulum without the dampening effect is 4 seconds. So we're going to develop a model that describes the position of the pendulum bob. B, use a graphing utility and graph the function. C, find the displacement of the bob at the start of the second oscillation. D, find out what happens to the displacement of the bob as time increases without bound. And so A says we have m equals 10, A equals 20, B equals 0.8. Since the period of the pendulum under simple harmonic motion is 4 seconds, we have 4 equals 2 pi over omega. So omega equals 2 pi over 4, or omega equals 2 pi over 2. So now let's take each of these pieces, M10, A20, B.8, and omega pi over 2, and throw them into our damped motion equation. So A is 20, B is 0.8, T is T, divided by 2 times the mass times the cosine of omega squared, so pi over 2 squared, minus b squared over our period times our mass squared. This is always 4 times the mass squared. So if we simplify that down, we get 20 times e to the negative 0.8t over 20. Cosine of pi squared over 4, because it's pi squared over 2 squared, which is 4. 0.8 squared is 0.64, and 4 times 10 squared is 400. Okay, so when you go to graph this, we actually will graph this function because of the way the curve is bounded. You graph this function as 20 e to the negative 0.8t over 20 times cosine t. And when you do that, you get a little graph that looks like this. That's dampening down to almost nothing. So figure 49 is that dampening motion. For C, it was asking what is the displacement of the bob at the start of the second oscillation. So we go down, up. So our second oscillation starts right here. It's approximately 17.05 centimeters. So mine isn't. Oh. All right, so let's look at D. D says, what happens to the displacement of the bob as time increases without bound? Well, just from looking at the picture, we know that it's going to dampen and eventually come to rest. But we can also look at this information here. Anytime you have an exponent, he is way more powerful than any cosine or sine. So, your function will follow whatever this exponential equation is going to do. So this exponential equation, as t gets bigger and bigger, it will give you a bigger and bigger negative exponent value, which means it's 1 over a really big number. 1 over a giant number is really close to 0, and that pushes our displacement closer and closer to 0 until it eventually comes to rest. Okay, when you have a function that follows neither one or the other properties, we can look at that as graphing the sum of two functions. So for example, if y equals, if I have f of x equals x plus the sine of x, I can look at the graph of x and look at the graph of sine of x. So here's y equals x, here's the sine function. We can truly just add the y coordinates to graph the addition of those two functions. So we say f of x equals f1 of x plus f2 of x. And we literally add the y coordinates together. So if x is equal to 0, y is equal to 0 here, sine of 0 is equal to 0, I add those two together and I get 0. When x is equal to pi over 2, our y equals x function is pi over 2, our sine function equals 1, and then the two added together is pi over 2 plus 1. and that's 2.57. So the graph, the point I graph on my graph is pi over 2 comma 2.57. When x is equal to pi, I get pi for my x function and 0 for my sine of x function. I add those two together and I get pi. So my next coordinate on my graph is pi comma pi. You do that with each of the major angles, and then put together a graph that is the combination of the two. So here we are at 0. It comes here to pi over 2, 2.57, goes through pi pi, hits at 3 pi over 2, 3.71, and 2 pi, 2 pi. So you just add the y coordinates together. Or okay, so we have f of x equals sine of x plus cosine of 2x. This also works for when I have a function with two trigs. So you just find the y coordinate, or what the y value is of each piece of the functions, and then add the two together to find the coordinate that goes on your graph. And that's it for today.